Hello everyone and welcome back to the C++ 3D game tutorial series. In this 31st video tutorial, we will see how to create the game engine. In particular, we will see how to reorganize properly all the source code files, how to improve in general the design of the systems created so far, and in the end, we will face the initial transformation of our current game framework in a game engine. As always, we will face three main parts: requirements, design, and implementation of all the necessary things to create a game engine. Let's start with the requirements. We need a C++ IDE. From this tutorial onwards, we will use Visual Studio 2019 Community, but any other C++ IDE could go well. However, Visual Studio is strongly recommended. The target platform is Windows, the target graphics API is DirectX 11, and last but not least, a bit of knowledge of C++ programming language is recommended. Now we can start the design part. Today we will deal with a very long tutorial. For this reason, we will face it in three distinct parts. In the first part, we will face the reorganization of the source code files. In the second part, instead, we will see how to improve the design of the systems created so far. And last but not least, in the third part, we will start to transform our current game framework in a game engine. Let's immediately start with the first part, the reorganization of the source code files. So far we have placed all the source code files inside a single folder, that is the project folder. Unfortunately, the number of files is increased drastically since the beginning of the series, and so we have to find a better way to manage them. One way is to separate the source code files in various folders following a specific criterion. Let's search for this criterion by exploiting our class diagram. This is our current situation. The big white rectangles that represent the packages have been already considered in our project in form of filters. From now on, we will consider them instead in form of concrete folders. Let's improve our diagram a bit more yet. The two main packages are the game engine and the app. Let's give a name to our game engine package and let's call it the X3D, where the X stands for DirectX. Let's call the app package instead game. At this point, let's simplify the names of the various packages. We can start by renaming the graphics engine package in graphics, the input system package in input. The math package is fine in this way. And in the end, let's rename the window in system package in window. What else? Well, let's rename the resource manager package in resource. And let's move it inside the X3D. Finally, since we want to consider the material a resource like texture and mesh, let's move the material class in the resource package. That's all. One last thing, that the X3D package should be represented concretely in two parts, the public API part and the private source code files. We will place the API, that is the application program interface, inside a specific folder called include. In our case, the API is represented by the set of header files created so far. We'll place instead the private source code files, like the C++ files, and in general all the other files we don't want to expose publicly, inside the source folder. Last but not least, we will move the libraries used by our engine contained in the libs folder inside the DX3D engine folder, and we will rename it in vendor. Very well, let's go ahead to the second part of the tutorial, that is about the improvement of the design of the systems created so far. The most important systems to improve from a design point of view are the graphics engine, the resource manager, and the input system. Graphics engine, along with the input system, have been designed as singleton classes. Despite in very few cases the singleton design pattern is really useful, most of the time it's better to avoid it. Generally, singletons are misused because they provide a global access to their instances through static methods. This feature leads the classes that depend on singletons to hide their dependencies. For example, here we have a class A that depends on singleton, but this dependency is not shown externally. It's hidden in the implementation of the constructor. This bad practice leads to the so-called code smells. If we expose the dependency through the interface instead, like in this case, we know with absolute certainty that the constructor of class A and the class A in general depends on the singleton class. Keep in mind that the singleton class here represents a generic class, not necessarily a singleton class. The approach just explained is another design pattern called dependency injection. The drawback of exposing dependencies in this way, though, is that we have to pass the dependencies as argument to a potentially huge number of methods. Since this won't be our case, we can use the dependency injection pattern without problems. Also, a singleton controls its instantiation. This is not something that we really want to provide to our graphics engine and input system classes. We want to have complete control over the creation and life cycle of our systems. In this way, we also respect the single responsibility principle. We have also tried previously to handle this aspect through the create and release methods. But even this way is not good enough. It also doesn't respect the RAII principle, necessary to support smart pointers. For all these reasons, we will completely remove the singleton pattern from graphics engine and input system classes. Also, from now on, we will handle all the DirectX 11 resources through smart pointers. In particular, we will use the COM-PTR smart pointers provided by the Windows SDK. In this way, the memory management will be handled easily, reducing nearly at zero the amount of memory leaks. At this point, let's talk about the resource manager. So far, we have created two resource managers, the mesh and texture managers, that handle respectively the mesh and texture resources. So, we have created a resource manager for each type of resource. Despite it could work on one end, on the other hand, this approach makes it really hard to manage the various types of resource at high level. For example, if we want to load a mesh, currently we have to get the mesh manager to load it. The same with the texture. What if we would use one and only one resource manager to load any kind of resource we can think about? We could call a method like createResource from file and retrieve the right resource we need through a template parameter. And that's exactly the way in which we will handle our resources from now on. This approach will allow us to remove the mesh and texture manager, simplifying a lot the design of our systems. Also, we will also able to handle in an easier way the introduction of new types of resources, like the material. The last system to take care of is the input system. We have already removed the singleton pattern from this system. In addition, we should remove the observer-listener pattern. We have used the observer pattern in order to notify of any input state changes to the app window class or any other listener. What if we will simplify the design of our input system by removing the listeners and by adding simple but effective methods like the ones we are seeing on the screen? By adding the isKeyDown and isKeyUp methods, we can simply ask the system about the state of the specific key or mouse button only when we need them, and we can retrieve the amount of movement of the cursor along the X and Y axis through the getDeltaMousePosition method. Obviously, these design decisions imply a bit of code refactoring of our input system, but at the end we will get a simplified and improved system. At this point we can finally talk about the initial transformation of our current game framework in a game engine. Before to start though, let's talk about the game framework. A game framework provides classes, interfaces, and/or systems that allow to simplify the creation of games. It simplifies the creation of games, yes, but at low level. So things like graphics APIs management, audio APIs management, resource management, input management, and so on are all handled by the game framework. So far we have created a set of systems like windowing system, render system, input system, and the resource manager. And it's exactly the union of these systems that is generally called game framework. But it's the duty of the developer to choose how to exploit and use those systems, all things that generally will be handled under the hood by a game engine. Indeed, a game engine does the big of the works for us, like levels management, entities management, the rendering of the meshes, the simulation of the lighting, the simulation of the physics, to name a few. That said, our current implementation is effectively a game framework. Very well, let's see how to start to transform it in a game engine. Let's start to add the game package and the game class. The game class can be considered the entry point of our game engine that will allow us to create and initialize all the systems by simply instantiating it in some point, for example in the main function. Also, the game class should provide a very important function called run, in which a while loop, also called game loop, will maintain our game in execution until the window is not closed. Another important class to add is the display class. This class should allow to combine together a window with a swap chain. Last but not least, by extending the game class we are able to create our own custom game class, like myGame, in which we'll be able to implement our own custom logic. I know there are a lot of topics to face, and exactly for this reason, if you have questions, doubts, or comments, don't hesitate to leave them in the comment section of this video or in the Discord server. The link to the Discord server is available in the video description. Also, if you find these tutorials helpful, please consider to support their development on Patreon. Every single contribution makes the difference, regardless the amount. Very well, we have gathered all the necessary information to start the implementation. Let's start by reorganizing the source code files. Let's click on Show All Files. In this way, we are able to manage directly files and folders in Solution Explorer. Now we have to temporarily exclude all the source code files from build. So let's select all the files by pressing Ctrl and A. And while we press Ctrl, let's left click only the elements that we have excluded from build so far. Very well, let's right click on the selected elements and let's select Exclude from Project. At this point, let's start to create the various folders. Let's start with the game folder. Then let's add the X3D folder. Then in the X3D folder, let's create the include folder for the public API. And then let's add also the source folder. In the end, let's move the libs folder inside the X3D folder. And let's rename it Inventor. So far so good, what else? Well, let's open the project properties. Here we should select the C++ version we want to use. Let's select the C++ 17 version. The next step to do is to change the include directories. So let's go to vC++ directories, and in the include directories field, let's start to modify the various paths. In particular, we have to change the libs/part in tx3d/vendor. From now on, let's use the slashes and not the backslashes. In this way, we use a format that is common across the various platforms, like macOS and Linux. Very well, let's do the same thing for the library directories. Last but not least, let's remember to add the include folder from which we will retrieve our API. Good, we can finally start to create the folders based on the packages added in the class diagram. So let's add the dx3d folder. Let's do the same things both in the include and source folders. Let's add one by one the various systems created so far. So let's start with the window. Let's move the window header file and C++ file inside their correspondent folders. Let's reinclude them in the project. Now it's arrived the time to improve our window class. First of all, we should remove from the public header files that represent the API of our engine all the included paths that are platform specific, like the Windows header file and so on. In this way, when other developers will use our API, he or she will have not to deal with the API of the internal libraries used by the engine. Very well, as we have seen in the introduction, things like gain loop, run method, and so on should be handled in a specific class like game. It's not the window task, so let's remove methods like isRun and broadcast. Here the rect type is not available anymore since it was something Win32 related. So let's replace it with our own rect class. So let's create the math package and let's move the rect header file inside it. At this point, we can include it in the window header file. We can finally replace the Win32 rect with our own one. Let's rename the getClientWindowRect method in getClientSize and the getSizeScreen in getScreenSize. Let's move the destructor method near the constructor in order to have a cleaner interface. Let's make it virtual. In this way, if we deal with pointers of the base class, in this case the window class, the destructors of the derived classes will be called as well. We can safely remove the broadcast method. HWND, like rect, is another Win32 type. We can replace it with a void pointer. We can safely remove even all the run-related things. Very well, the interface of the window is ready. Let's deal with the implementation. Here we have included the window header file in this way. Despite the double quotes include format could work on one end, on the other end the angled brackets approach should be less ambiguous to the reader, especially if we are trying to create a library. So let's use the angled brackets format. Pay attention here, since we have used this type of include directive Across all the source code files, we have to replace all its occurrences with the new format. To do this in the least painful way possible, let's select the include directive and let's press the Ctrl F. At this point, the quick find window should appear. In the replace field, let's write the angle brackets format. Let's select the entire solution option and in the end let's press the replace all button. This is something we will do often during the tutorial. Now we have to re-include the Windows header file here in order to use the Win32 API. So far so good, let's comment for now the post quit message. At this point we can focus on the window constructor. Let's simplify the code a little bit. Let's initialize the WND class X data structure with the list initialization feature that consists to add a braced init list. Here the only properties we need are the size, the class name, and the pointer to the window procedure. Let's also use the Unicode character set from now on. Very well, here register class X returns the ID of the registered class. Let's retrieve it. If the class ID retrieved is 0, then no class has been registered, so let's throw an exception. We can improve the way in which we handle the exception, and to do that, let's take the prerequisites header file and let's place it inside the tx3d folder. Here we can define some important macros to handle the exceptions. Let's include the iostream and stdaccept header files. Let's define the dx3d error macro. And let's add the message parameter. With this macro, we want to provide to the user a way to print log messages and throw exceptions. Let's print log messages through the so-called vclog global object. Let's throw exception through the standard runtime error object. Like for the errors, let's do the same thing for the warning and information messages. In these cases, let's use only the wclog. So far so good, let's come back to the Windows C++ file and here let's replace the throw standard exception with the x3d error macro. Obviously, let's include the prerequisites header file. At this point we should create the window, but there is another thing to take care about, the correct computation of the size of the client part of the window. This can be done by calling the adjust window rect win32 function. This function requires a rect object in which we have to place the desired size of the client. Let's use the usual 1024 pixels per 768 pixels. Here we have to pass the style used to create the window, in this case the WS overlapped window. At the end, let's pass false since we don't use any menu. Good! Here we can remove the WSX overlapped window. Here, instead, we should use the class name used previously, but we can also exploit the class ID retrieved previously by using the makeIntAtom macro. The title of the window is fine in this way, but I changed it a little bit yet. In the end, let's use the size computed previously. If the createWindowX function fails, the HWND attribute should be 0. In that case, let's call the X3D error. Good! Let's take the setWindowLongPointer function from the broadcast method. And let's place it here. This function allows to provide the pointer of our window instance to the window procedure. Pay attention here, since we are using a void pointer for the window handle, and since the various win32 function accepts only the HWND type, we have to cast it, and let's do it with the static cast keyword. So far so good, since the code inside broadcast method will be useful when we will create the game class, for now let's simply comment it. What else? Well, we have to improve the getClientSize and getScreenSize methods. Here we have to initialize the rect data structure, cast the window handle to HWND, and pass it to all the various win32 functions. In the end, let's return our own rect object. We can do this by using again the list initialization feature of C++. Let's do the same thing for the getScreenSize. Last but not least, in the window destructor, let's call the destroyWindow function. Very well, it's finally the turn of the game class, so let's create the game folders and the game class. To speed up the creation process, let's copy-paste the window header file into the game header file. Let's remove all the unnecessary things and at the end let's add a forward declaration to the window class. Forward declaration allows us to avoid to include header files in the public API that could include in turn private stuff. This is not the case for the window class, but as a general rule of thumb, let's always add a forward declaration for each class we want to expose publicly, and let's try always to include the header files only in the C++ files, obviously where possible. Very well, let's finally add a unique pointer of type window and let's instantiate it inside the game constructor through the utility function makeUnique. At this point we can finally create the run method. Since this function is generally Win32 platform specific, let's create a Win32 folder inside game folder, and let's create a Win32 game C++ file. Here we are only to place the implementation for run method. Since it is nearly identical to the previous broadcast method of the window class, let's copy-paste its code. Let's improve our code with the same improvements applied so far to the window class. As we have discussed in the introduction, we have to add a while loop. That is, the game loop that should maintain our game in execution until something allows us to exit from the loop. This can be done by adding a boolean flag like is running in a game class. Let's initialize it as true. Let's place it in the while loop condition. At this point, the loop ends only when the isRunning flag is set to false. When we should set the flag to false? We could send a W and quit message when the window is closed. And when we receive here the message, we can set the isRunning flag to false. Well, at this point we can take the main C++ file and place it inside the game folder. That is our final application. Here, let's include the game header file and let's remove all the code related to the graphics engine and input system. Let's call the run method and let's return -1 if an exception is catched. Now, let's see how to send the WM quit message. We have only to handle the WM close message in the window procedure, message sent when the close button of the window is clicked, and at that point we can call the post quit message. This Win32 function sends the WM quit message to the game loop. So far so good, let's see if it works. And it works very well. It's the turn of the graphics engine. Let's start by creating the graphics folder. At this point, let's hold the Ctrl key and let's select one by one all the header and C++ files of the graphics classes. Let's move all of them inside of the graphics folders. Let's start to improve the graphics engine class. For the moment, let's comment the include directives. As we have already discussed in the introduction, we have to remove the singleton pattern. So let's make constructor and destructor public. And let's remove everything but the render system attribute and the get render system method. The reason behind it will be clear in few moments. Very well, let's start to replace the included prerequisites header file, and as we have already done previously, let's press the Ctrl F keys. At this point, let's handle the instance of our render system with a unique pointer. In the graphics engine C++ file, let's start to replace the various include directives as usual. The exception header file is not necessary anymore since it is handled in the prerequisites header file. At this point, let's remove everything. Let's leave only an empty constructor, an empty destructor, and the getRenderSystem method. In the constructor, we can finally create our render system through the makeUnique function. Let's go ahead and let's include in the project the render system files. In the render system header file, let's remove the feature level that is not necessary here. Now we have to start to replace all these row pointers of the various DirectX 11 resources with the smart pointer ones. To do that, let's select the include directive of the D3D11 header file and let's replace it by adding a further header called WRL. WRL is the Windows Runtime C++ template library, and it provides the so-called COM-PTR smart pointer. This type of smart pointer is provided to handle the so-called COM resources like the DirectX 11 ones. Let's start to use it for the ID3D11 device. Since we want to try to speed up a bit the entire replacing process, let's press again Ctrl F to use the quick find feature. So let's replace the prefix ID3D11 with the one with the pre-appended COM-PTR. Pay attention here. DirectX text header file is also modified during this process because it contains DirectX resources. So let's find the Open tab of DirectX text header file, in this case is the first tab, and close it without saving it. Very well, let's polish the result by adding the final angle brackets. At this point, let's do the same process for the ID XGI and ID3D block pointers. So far so good. Yet again, let's replace the include directives. What else? Well, let's provide again the feature level attribute removed previously. And let's fix the comptr added erroneously by the replacing process. One last thing, since now we are using smart pointers, if we want to retrieve their raw counterparts, we have to use the get function, like in this case. Very well, we can finally start to fix the device context class. From now on, we will try to remove the destructors where possible, since they were used mainly to release the DirectX 11 resources, but now this aspect is all handled by the smart pointers. If we jump into the device context C++ file, we can see that we have to fix all the other graphics resources before to proceed. So let's start by including again all the graphics classes in the project. And let's start to fix the constant buffer class. Now we can fix the index buffer. Let's fix the pixel shader. Let's also fix the swap chain class. Then we have the vertex buffer class. And last but not least, let's finally fix the vertex shader class. So far so good, let's go back to the device context and let's fix the remaining issues. The main issues are related to the conversion between smart to raw pointers, so let's call the get method. For now, let's comment all the parts related to the texture resource. Let's see if we are able to compile the project. Unfortunately, no, we have a compile error. This kind of errors are not so easy to find out, so please pay attention. When we use variadic templated function like make unique, make shared, and so on, and we provide wrong parameters, the IntelliSense is not able to inform us about the issues, so we are able to discover the problem only after we have compiled the project. Like in this case. In this case, we have to get the raw pointer of device context. At this point, let's create our graphics engine in the game class. Let's retrieve the raw pointer of graphics engine by adding a getGraphicsEngine method in the game class. What's the next step to do? Well, we could create the display class in such a way to connect the window with a swap chain. Let's add a pointer to a swap chain. In the display constructor, we should find a way to access the graphics engine, in particular the render system, in order to create the swap chain. Previously, we have resolved this issue by providing a global access to the graphics engine, but as we have already discussed in the introduction, this approach leads to various problems. To solve this issue, we could use the dependency injection pattern. So let's start to add a pointer of the game class in the display constructor as parameter. At this point, we are able to access the render system without the need to provide global accesses. Let's inherit from window class and let's retrieve the window handle. At the end, let's also provide the client size. We can put a breakpoint here, for example, so that we are able to see how the things are going under the hood. Last but not least, don't forget to effectively instantiate the display class in the game class. Let's see if it works. Very well, it seems to work. Unfortunately, we have a problem when we close the window. We have forgotten to remove the content of the render system destructor. Let's do it and let's see if it finally works. And it works. This is a good but approximate sign that all the resources, most of all the DirectX resources, have been correctly unloaded. We can finally start to deal with the resource managers and the resources. So let's create the resource folders. And let's select and move all the resources classes inside it. At this point, let's start to include the resource manager in the project. As we have seen in the introduction, since we want to give to the user the ability to choose what kind of resource to retrieve, let's start to implement a template function from the createResourceFromFile method. Now we should return a generic shared pointer object of type T, where T represents the type of the resource we want to retrieve. Then, in the createResourceFromFileConcrete method, let's now return a resource smart pointer. Let's remove the virtual keyword from the structure and create a resource from FileConcrete. The only thing we have to do in the createResourceFromFile method is to make a dynamic cast from the generic resource pointer retrieved from the createResourceFromFileConcrete to the specific resource pointer specified by the user through the T parameter. This T parameter can be the mesh, the texture, the material, or any other type of resource. Let's go ahead and let's fix the Resource Manager C++ file. Here the only thing that we have to do is to fix and to implement the create resource from file concrete. Let's add a file system path object and let's call it resource path. Here let's place the path string. Here let's check if the resource has been already created previously. If that is not the case, let's check if this file actually exists by using the file system exists function. Here let's pass the just created resource path object. If the file doesn't exist, let's return a null pointer. At this point, we should handle the creation of the resources in a different way. First of all, let's get the extension for the file we are going to process by calling the extension method. Then let's make a check. If the extension is equal to .obj, that means we have to process a mesh, so we should create a shared pointer to a mesh instance. Before to do that though, let's start to fix the resource and mesh classes. The resource class is fine in this way. Let's only add a row pointer to the resource manager as parameter in the constructor. This will be useful later when we will have to access the various systems from the resources. So far so good. Now we can start to fix the mesh class. Here we have many math classes to fix yet, so let's select the vector 2D, the vector 3D, the vector 4D, the vertex mesh and matrix 4x4 classes, and let's move them inside the math folder. Obviously, let's include them in the project. At this point, let's go ahead with the usual replacing process. Very well, what's the next step to do? Well, we have to add the resource manager row pointer as parameter in the mesh constructor, as we have done with the resource class. Let's remove the get vertex and index buffer that we don't want to expose publicly. In the end, let's return a copy and not a reference of material slot from the getMaterialSlot method. Cool, let's go to fix the mesh C++ file. Yet again, let's replace the include directives. Let's fix the constructor and let's pass the resource manager pointer to the resource constructor. Let's do the same thing even with the other constructor. At this point, let's improve the implementation of the first constructor. The most important improvement to do here is to convert the wide-char string to a char string. In the previous versions of C++, it was a mess to deal with this kind of things. Now we can easily make the conversion with the file system path object. We have only to create the path object passing the wide-char string, and in the end, if we call the string method, we get a simple char string that we can use easily with the load_obj function of the tiny obj loader library. So far so good, let's remove the getVertex and indexBuffer method and let's fix the getMaterialSlot method. At this point we have to fix many things related to the graphics classes. In particular, let's go to the render system class and let's start to fix the part in which we have to compile the shader used to create the input layout. As we have seen in the previous tutorials, the input layout is necessary to inform the graphics API about the data layout used in the vertex buffer. So let's create an array of unsigned chars and let's call it mesh layout bytecode. Here we will place the compiled shader bytecode. Then let's store the size in bytes of the compiled shader in the mesh layout size attribute. Let's add a method in which to compile this shader, and let's call it compile private shaders. Good, let's implement it. Let's reuse the code written in the compile vertex shader method. At this point, let's start to use the smart pointer for the blob resources. Since we really don't want to expose this shader publicly, we can place the code directly here using the raw string literal in this way. We have only to place the code inside the rounded brackets. So let's go to the vertex mesh layout shader.hlsl file and let's copy paste the code. That's all, let's get the size of the source code through the strlen function. What else? Let's don't call the d3d compile from file function, but the d3d compile function. This function allows to compile shader code directly from memory. We are only to pass the pointer to the shader code and the size of the shader code, an optional name for the shader, then we can replace the entry point name with the name used for the vertex shader function, so vs main. In the end, let's fix the blob and error blob variables. At this point, if the function fails, let's throw an error. Otherwise, we can copy the code in the mesh layout by code attribute and store its size in the mesh layout size. As last thing, let's remember to call the compile private shaders during the render system constructor. At this point, let's fix the vertex buffer. We have to remove all the vertex buffer constructor parameters related to the input layout shader code. Last but not least, let's pass the shader bytecode stored in the render system to the createInputLayout method. So far so good, we can finally turn back to the mesh C++ file, and here we can start to fix the creation of the vertex buffer. To do that, we have to retrieve the render system. We can do that by retrieving the resource manager. From the resource manager, we should get the game instance, but currently we are not able to retrieve any game instance. So let's go to the resource manager and let's add to the constructor a pointer of a game instance as parameter. Then let's retrieve it through a getGame method. Good, let's come back to the mesh C++ file and now we are able to access the game instance, the graphics engine instance, and finally the render system instance. At this point we are able to create the vertex buffer. Let's do the same thing for the index buffer. Here we have a problem though. We should fix the create vertex buffer method in the render system class. Let's do it. In the implementation, let's remove all this useless code and let's simply return the object returned from the make shared. Good, let's come back again in the mesh C++ file and let's fix all the remaining issues. Very well, the mesh is ready. Let's come back to the Resource Manager C++ file and finally we can start to create a mesh instance. Obviously, let's pass the path and the Resource Manager instance. If we have a valid pointer, we can store it inside our map, and we can finally provide the resource externally. Good, it's finally the time to instantiate the resource manager in the game class. So let's make a unique pointer to the resource manager and pay attention here. The order in which we define the various unique pointers is important. In this case, when the game instance is destroyed, the first to be deallocated is the resource manager, the second is the display, and the third and last one is the graphics engine. Good, let's finally create the resource manager with the make unique function. At this point we can test the resource manager. Let's create a mesh from the file house.obj that is placed in the assets/meshes path. Let's put a breakpoint near the create resource from file function and let's compile it. Everything seems to work in the right way. And once we close the window, everything seems to be unloaded correctly. It's the turn of the texture. So let's move the texture files from the resource folder to the graphics folder and let's rename it in texture 2D. As usual, let's fix the various includes directives. Be sure to remove the resource base class. And let's transform the enum type in enum class type. Let's fix all the smart pointers. At this point, let's fix the C++ file. Since texture 2D is now a render system resource, let's add the pointer to the render system instance as parameter in the constructor. Let's replace the old way to access the render system with the new one, that consists simply to access the system attribute. In order to access the private variables of the render system class, let's make texture2D a friend class of the render system class. What else? We can start to fix the types defined in the texture2D type enum. At this point, let's replace again the access to the render system. So far so good, we can finally go to the render system class, and here we can start to add the two create texture methods, one related to the first constructor that allows to load a texture from file, and the other one related to the second constructor that should allow to create the so-called render targets. At this point, let's include the texture2D header file and let's add a forward declaration to the texture2D and texture2D pointer in the prerequisites header file. In the end, let's turn back to the render system and let's implement the two create texture methods. Let's create the texture2D resources as we have already done previously with the other graphics resources. Here we have finished. Let's create another class in the resource folder and let's call it texture without 2D. This will be the high-level texture resource that will cover under the hood all the ugly internal things. Let's copy and paste the mesh header file in the texture header file. Let's remove all the useless code. And let's leave only the constructor. In the end, let's add a texture 2D shade pointers as attribute. In the end, let's implement the constructor and let's create the texture 2D by retrieving the render system class, as we have done previously with the mesh class. In the end, let's come back to the resource manager and, as we have already done with the mesh, let's check if the extension of the file path passed as parameter is a .jpg, a .png and a .bmp, and so on. If that is the case, let's create the texture resource. Here we can simplify a bit the code and move the part in which we place the resource inside the map after we have created the specific resource. Very good! Last but not least, let's go to the game class and let's try to load the wood.jpg texture. Let's see if it works. And everything seems to work properly. We can finally start to fix the material class. As first thing, let's include the header and C++ files in the project. In the material header file, let's copy all these selected include directives and let's pass them in the C++ file. In the header file, let's include only the resource header file. Then, let's make the material an extended class of resource. At this point, let's improve the constructor and let's replace the parameters with the path string and the pointer to the resource manager, in the same way we have already done with the other resources. Let's also add a pointer to the resource manager in the second constructor as parameter. Let's go to the material C++ file and here let's fix the parameters of the various constructors. Let's replace the include directives of material. As next step, let's pass the various parameter to the base class constructor. We can finally start to fix the constructor implementation. The first thing to do here is to improve the creation of the vertex and pixel shaders. So, let's go to the vertex shader header file. And here let's add two parameters. And here let's add the two parameters in the constructor, the path to the shader and the name of the entry point of the function to compile. At this point we can improve the implementation of the vertex shader by copying the code we have already written in the compile private shaders method of the render system class. Since in this case we are going to compile the source code of the shader from file, let's use the d3d compile from file function. Let's remember to include the d3d compiler header file. In this case, we have only to check if there is something in the error blob, and if that is the case, let's print the various errors or warning messages by using the getBufferPointer method. If the blob pointer is empty, let's throw an exception. In the end, let's replace the succeed with a more suitable failed macro, and if the create vertex shader function fails, let's throw, even in this case, an exception. Since the code we have just written is practically identical to the one we should use for pixel shader, let's copy and paste it even there. Let's also add in the pixel shader constructor the same parameters used in the vertex shader constructor. At this point, the only thing to change are the vs underscore phi underscore 0 to ps underscore 5 underscore 0 and all the occurrences of the vertex shader in pixel shaders. Let's copy the parameters of the constructor and let's use them in the create vertex and pixel shader methods of the render system class. Let's fix the C++ file as well. Let's also exploit this moment to improve the way in which we create and return the various graphics classes. Let's simply return the result of the makeShared function in the various create methods. At this point, compile vertex shader, compile pixel shader, and release compiled shader methods can be removed. Let's comment them for the moment. Let's also comment them in the header file. In the end, let's turn back to the material C++ file and, as we have already done with the other resources, let's retrieve the render system and let's create the various shaders. Let's do the same thing in the setData method. Last but not least, let's create the resource in the Resource Manager only if the extension of the file corresponds to HLSL or FX. Let's also handle the case in which we have already created a material from the same shader file. In that case, let's simply create another material instance using the same shaders created previously. The final thing to do is to test the creation of the material in the game class. Let's start to create a shader file. So let's go to the Assets folder and here let's create a Shaders folder. Here let's create my material.hlsl file. Here we will place the code of the shaders of our material. Since we have just written a lot of shader code, let's copy and paste the vertex shader from dir lightbump vs.hlsl file. Here, in vs underscore output data structure, let's leave only the position and text chord attributes. In the constant buffer, instead, let's leave only the word, the view and the projection matrices. In the end, in the vs main function, let's leave only the code related to the position and text chord attributes. One more thing to do is to add the pixel shader code. Let's get it from the pixelshader.hlsl file. You can find the mymaterial.hlsl source code file in the Assets and Libs branch of the GitHub repository. You can find the link to the branch in the video description. Let's remember to remove the material destructor. At this point, we can finally try to compile and debug it. It seems to work very well. We have fixed a lot of systems so far. At this point, let's start to clear the content of our window with a red color. To do that, let's go to the game class and let's add the so-called callback methods. So the onCreate method that should be called when the game is initialized, the onUpdate method that should be called at each iteration of the game loop, and last but not least, let's add the onQuit method that should be called instead after we exit from the game loop. What else? We should add a private method called onInternalUpdate. That is the same of the onUpdate one, but here we will handle the update of all our internal system. So the update of the graphics engine, the input system, and so on. At this point, let's call these callback methods in the run method. Last but not least, let's add also a quit method, in such a way to force the closing of the game at any time, not only when the window is closed. Good, now that we have an onUpdate callback method, we can start to see how to clear the content of our window at each iteration. The first thing to do is to go to the graphics engine class, and here we have to add the update method. This function should allow us to render a frame each time it is called. Now, what do we have to do? We should clear the content of our window, but we are not currently able to access the instance of our window. To do that, today we will adopt a simple approach based on the usage of the game instance, for which we will retrieve the display and so the swap chain object. We will improve this approach in the next tutorials. So let's pass a pointer to the game instance in the graphics engine constructor as parameter. In order to access the private stuff of the game, let's make graphics engine a friend class of the game class. In the update method of the graphics engine class, let's retrieve the display instance. Even in this case, we have to make graphics engine a friend class of the display class. At this point, we are able to use our swap chain. So let's go to our device context from render system class and let's call the clear render target color method. Good, at this point we have to fix again our device context class. We have to be careful about the way in which we pass the smart pointers to the various directX functions. For now, let's simply save the raw pointers to specific variables, and let's pass them to the various functions. At this point, we can simplify the way in which we set the constant buffer. We can simply use one single method in which we pass only the constant buffer object and nothing else. Then we set the constant buffer for both the vertex and pixel shaders. Good, let's come back to the graphics engine class, and in the update function, let's start to set the viewport size. This can be done by retrieving the client size of our window. Last but not least, let's call the present function. In the end, let's come back to the game class, and in the constructor, let's pass the game instance to the constructor of the graphics engine class. Don't forget to call the update method of the graphics engine class in the onInternalUpdate callback method. Let's see if it works. And it works! This has been a very long tutorial, but hold on, we have nearly finished. It's around the time to test the rendering of a mesh. So let's go to the graphics engine header file and let's add a data structure called mesh data. Here let's place two important attributes, the mesh pointer and the material pointer. Through these two resources, we can easily start to render our mesh on the screen. As a temporary thing, let's pass this structure as parameter in the update method. Let's remember that this structure is for test only. We will remove it as soon as possible. What else? Well, we have to load these resources somewhere. Let's do this in the game class. In particular, let's add a mesh pointer attribute and a material pointer attribute. In these attributes, let's store the resources we are currently loading inside the game constructor. Let's also add the texture inside the material. In the end, let's pass the mesh and material resources as parameters to the update function of the graphics engine class. Let's start to use these resources inside the update function. As first thing, let's bind the vertex buffer to the graphics pipeline. As usual, in order to get the private stuff of the mesh class, let's make graphics engine a friend class of the mesh class. Good, let's do the same thing for the index buffer. At this point, we can handle the rendering of the various parts of the mesh subdivided per material slot. So, for each material slot, let's set the vertex and pixel shaders of the various materials. Then let's retrieve the data of the material slot at the specified index. And let's use this data to draw the specific part of the mesh with that material. Perfect! Obviously, in order to correctly render our mesh, we have to go to our My Material shader, and here we have to copy the constant structure. Let's paste it in the graphics engine C++ file. As a very first thing, let's set an alignment in the memory of this structure of 16 bytes. This is necessary in order to allow the graphics API to handle the data correctly. This structure contains the word, the view and the projection metrics attributes, so let's use our own metrics 4x4 class to handle them. At this point, let's come back to the update function, and here let's start to set our matrices. In particular, let's set a rotation matrix along the y-axis in the word matrix. Let's set a translation matrix of -10 units along the z-axis in the view matrix. And don't forget to invert it with the inverse method. Last but not least, let's make a perspective projection matrix. The only thing that remains to do is to store the constant data structure to the constant buffer of the material through the setData method. In the end, let's bind the constant buffer to the graphics pipeline. Let's see if it works. And it works! There are many things to polish yet, but this is already a big result. Now it's the turn to apply the textures over the surfaces of our mesh. So let's start by calling the set texture of the device context. But we haven't fixed it yet, so let's go to the device context class, and here let's use only one set texture method, in which we use only the array of the texture 2D pointers and the size of the array. In the device context C++ file, let's reuse the code written previously. Let's fix the erroneously added smart pointers. And let's retrieve the row pointer through the get method. Let's bind the textures to the graphics pipeline for both the vertex and pixel shaders. Good, let's come back to the game class and let's finally pass the textures of our material. Here there is a problem though. The method accepts only the texture 2D and not the texture pointers. So we have to fix this issue by going to the material class and convert the vector of textures pointer from texture PTR to texture 2D PTR. This is not the best way to handle this aspect, but we will improve it in the next tutorials. For now, let's try to see if it works. And it works! What's the next step to do? Well, let's go to the constant buffer C++ file, and here we could start to replace all the occurrences of the exception with our own dx3d error macro. Good, as last thing, let's fix the proportion of the viewport. So let's go to the graphics engine C++ file and let's cast the width and height to float in the set perspective projection method. Another important thing to do now is to handle the resize of our window. So let's go to the display header file and let's start to override the onSize callback method of the window class. Let's also improve the method by passing a rect parameter through which we can pass the new size of the window. In particular, in the Windows C++ file, when we handle the WNSize message, let's pass the value returned by the getClientSize method. At this point, let's implement the onSize method of the display class. As first thing, we should inform the game class about the resizing of the window. So let's go to the game class and let's add another callback method called onDisplaySize. By handling this event here, we are able to render our scene even during the resize of the window. Let's remember that when we resize the window, a lot of Win32 messages are processed, so the game loop is generally locked until the resizing is not finished, preventing us to rendering continuously our scene. Good, let's call on internal update in the onDisplaySize method. At this point, let's come back to the onSize method of the display class and let's call the onDisplaySize method. Obviously, don't forget to make display a friend class of the game class. Last but not least, each time we resize the window, we have to resize the buffers of the swap chain accordingly. As a last thing, let's fix the way in which we reset the smart pointers in the swap chain class. Good, let's see if it works. And it works. The scene is rendered even during the resize. Well, we are practically finished. Let's move the old stuff in an old folder. The last system we have to fix yet is the input system. So let's start by creating the input folders. Let's move the input system and source code files from the old folder to the input folder. As we have discussed in the introduction, let's remove all the stuff related to the singleton pattern and observe all listener pattern. Let's leave only the constructor and destructor methods, the update method, and let's remove the set of listeners. Let's transform the old mouse position in vector 2D, and as last thing, let's remove the first time flag and the static pointer. Good! In the input C++ file, let's start to fix the include directives. Then let's remove all the methods but the constructor, the destructor and the update methods. At this point, let's start to handle the keyboard input events. So let's comment, for now, the mouse management part. Here the loop is fine. Let's only remove the code based on the listeners. Let's come back to the header file and let's add a further array of the case states, and let's call it final case states. This array will hold the various input states of all the keys until the next call to the update function. We are talking about key down state and key up state. So when the key is down, we store a 0 value. When the key is up, we store the 1 value. If instead the key is not down and the previous state is equivalent to the current state, we are in a sort of rest position. For this kind of state, let's set the 2 value. What else? Well, let's start to add the isKeyDown and isKeyUp methods. For these methods, we can ask to the input system about the current state of a specific key. Obviously, we have to define an enum in the prerequisite header file, and we have to call it key. Here we can start to define the main keys, so the letters, the numbers, and the special keys like escape, shift, space, and enter. For now, these keys are enough. So let's use this enum class as parameter for the isKeyDown and isKeyUp methods. What do we have to do here? We have to convert our own keys to the Win32 ones. So if our own key is in the range between the letter A and the letter Z, we have to retrieve the correspondent Windows key code used by the Win32 functions. The same for the numbers, and the same way we handle the special keys. In the end, let's check if the state of the specific key is equivalent to 0. In that case, the key is down. At this point, we could do the same thing for the isKeyUp, but let's move the computation of the Win32 key code in a more suitable function that we can call getInternalKeyCode. As last thing, let's leave only the check and let's retrieve the key code by simply calling the getInternalKeyCode method. Let's do the same thing for the isKeyUp. In this case, let's check if the value is equivalent to 1. Good, we can start to test our input system, so let's go to the game class and let's instantiate it. What do we have to do now? We have to call the update function of input system inside the onInternal update method. After that, we could check if the enter key is down. And in that case, we can print an info message in the console output. If we press the enter key, a series of messages are printed on the console. Cool, it works! Let's test now the isKeyUp method. Very well, it works as well. Good, what's the next step to face? We have to manage the mouse input events. So let's go to the input system C++ file and let's uncomment the mouse management part. As we have done previously, let's remove all the code related to the listeners. At this point, let's add the delta mouse position attribute and the getDeltaMousePosition method. In the delta mouse position attribute, we have to do nothing but to store the difference between the current mouse position and the old one. That is all we need to handle the mouse movements. If there is no variation between the current and the old mouse position, let's simply set the delta mouse position at 0. Let's turn back to the game class and let's check if the getDeltaMousePosition works by printing a message with the X and Y values. And it works! As last thing, let's lock the cursor at the center of the window, in such a way to prevent to click outside the window and so to provide focus to other applications. Let's add the lock cursor and set lock area methods. Then let's add a cursor locked flag. Let's add the lock area attribute, that in general should be the size of the window, and let's also store the center of this area, that will be the point in which we will lock the cursor. Let's start to implement the lock cursor and set lock area methods. In the end, in the update method, If the cursor is not locked, let's compute the old mouse position as we have already done previously. If the cursor is locked, instead, let's set the cursor position at the center of the provided locked area. And obviously, the old mouse position is nothing more but the center of this area. Let's finally test it in the game class. So in the game constructor, let's set the lock area, that is the size of the window. Let's only handle the top and the left of the client area of our window in the Windows C++ file. Let's come back to the game class and let's lock the cursor. Let's also set the lock area when we resize the window. Let's see if it works. And it works! That's all we have finished to improve our system. Let's only make a bit of tests yet. If we press escape, we want to unlock the cursor. Instead, if we press enter, we want to lock the cursor. Good, it works. We have forgotten to handle the mouse buttons, so let's go to prerequisites header file and in the key enum class, let's add the left mouse button, middle mouse button and right mouse button. let's extend the game class and let's create our own MyGame class. Let's instantiate it in the main function. That's all for now, folks. Today we have seen how to start to create our game engine, and we have done it by improving also a lot all the systems created so far. In the next episode we will face the creation of the entity system. I hope you enjoyed this video. See you soon. Thanks for watching.